Hello and welcome. Today let's talk chapter 2. We'll get into some chemistry here and we'll check out and we'll see how chemistry will come alive basically in this chapter now. Now here when we start this chapter, first thing we want to discuss is the term matter. When we talk about matter, matter is anything that occupies space and has a mass. Anything that occupies space and has a mass. Now, mass is different than weight. Mass is different than weight. Mass, you'll see, is the measurement of the amount of matter that an object contains. When we talk weight, weight we'll see is going to be the measurement of the pull of gravity on an object. Now, when we talk about the mass of an object, I'd like you to know the mass of an object is going to be equal to the actual amount of matter in the object as we described. It's equal to the actual amount of matter in the object. Now, when we talk about mass, I would like you to know that mass is going to remain constant. The mass of an object will remain constant wherever that object is. For example, your mass is the same at sea level as it is on a mountaintop. And when we go through and we talk about weight, we'll see your weight is going to be slightly less on the mountaintop. And that's going to be because of gravitational forces that are going to be acting on the body. We compare mass to an object's weight. You will see the weight of an object varies with gravity. Now, when we talk about matter, matter exists in 3 states. It exists in 4 states, but we're going to talk about 3 in relation to the body. Now, when we talk about 4 states, those 4 states will include solid, liquid, gas, and plasma. But like I said, we'll talk about the 3 that we've got listed here more in relation to the body. Now, example of each can be found in the body. For example, we'll see when we talk about solid, solid will be a structure that contains a definite shape and a volume. And an example will be our teeth. Our teeth are solid. When we talk liquid, liquid objects will have a changeable shape to them. They will have a changeable shape and they have a definite volume. And when we talk liquid, an example of liquid would be blood. Blood. Here's just one example. Now we talk gas. Gas, air we breathe. Gas has a changeable shape as we can see. And volume as well. And volume. Now when we go through and we talk about the next term we're going to go through, we're going to look at is going to be energy. So let's just move over this periodic table of elements here and here, and we'll come back and we're going to talk about these and we're going to look at them in greater detail. No, the next term, as I described, is going to be the term energy. Now, when we talk energy, energy is going to be defined as the capacity to do work. It is defined as the capacity to do work, or it's going to be defined as the capacity to put matter into motion. As the capacity to do work or put matter into motion. Energy is the mover of substances. It is the mover of substances. Now we talk about energy, so the greater the work done, the more energy used to do that work. The more work done, you'll see the more energy was used. For example, if we have an individual who has to move a refrigerator, let's say 1 story up, versus an individual who has to move it up 2 stories where there's no elevators. So more work done, more energy used. You could see there. Same thing here we could see with the baseball player. If a baseball player comes in and hits a home run, more energy is used to hit that home run versus a baseball player that comes in and just, let's say, bunts the ball. Okay? Now, when we talk about energy, energy is going to exist in two forms. It'll exist in two forms. Energy exists in two forms. One type of energy I'd like you to know about is going to be kinetic energy. And the second type will be potential energy. Now, when we talk about kinetic energy is going to be actual energy in action, energy in motion. Versus when we talk about potential energy, potential energy, just like the name says, it's potential energy. It has the potential to bring about a change. So it is stored energy. It's inactive energy as we can see. Stored energy. Now, when we talk, basically, it's energy that has the potential or the capability to do work. Okay, but presently, it is not doing so. So that is potential energy. For example, would be, let's say, batteries in something that's not being used. Let's say I've got a flashlight. Turn the flashlight off. When the flashlight is off, the batteries now have potential energy. That energy inside the batteries is potential energy. It's not being used. But let's say I turn the flashlight on. When you turn the flashlight on, now that energy is being used, so that energy now is kinetic energy. So we can see energy can be transformed from potential to kinetic energy. Same thing with a dam. Water, when it's confined behind a dam, is potential energy. All right, when that water starts to come down the dam, we've got special equipment we can put together and have turbines there that could collect that energy, and we could use that same energy then that's going to be basically that's going to be picked up when this water is falling down the dam, and it could be used to give electricity to towns. So that is potential energy. Same thing in your legs. In your legs, you have potential energy, right? Somebody tells you, okay, get up and let's go run a mile. Obviously, you're all going to say no, but if we say, oh, we'll give you some extra credit points, maybe some, 15 extra credit points, maybe 25 extra credit points, you have to show me a video of you actually running 1 mile. And my email is going to be flooded with videos. So potential energy is what you have in your legs as well, right? So just a few examples. Now, when potential energy is released, it becomes kinetic energy. It becomes kinetic energy, as we saw, and it's capable of doing work. I gave you that example of the flashlight, the legs, right? And then the dam, and so forth. Next, then, let's talk the different forms of energy. I want you to know energy is also going to be found as chemical energy, electrical energy, and we can see mechanical energy, and also radiant or electromagnetic energy. First, let's talk chemical energy. Now, when we talk chemical energy, as we can see here, chemical energy is going to be energy that's going to be stored in the bonds of chemical substances. It's going to be energy that's stored in the bonds of chemical substances. So again, you can say chemical energy is the form of energy stored in the bonds of chemical substances. Now, when chemical reactions occur, right, when chemical reactions take place, they rearrange chemicals and it causes the potential energy to be released, and then it becomes kinetic energy. Here, when we talk, some of the energy in food, we'll see our foods have energy, right? That's why we eat food, because we need the energy. So here when we talk, some of the energy in foods is captured temporarily in the bonds of a chemical that we call ATP, adenosine triphosphate, ATP. Later, ATP's bonds are going to be broken, and that stored energy is going to be released. That stored energy is going to be released, and it's able to do cellular work. It's able to allow our muscles to contract or allow our muscles to relax. It's available to allow things to move in and out of the cell, right? So ATP we'll see is going to be the most useful form of energy in living substances, and it runs almost all functional processes like I've just described now. ATP. There's another form of energy we find in the body as well, GTP, but we won't be, this is, introductory course in physio, your first course in physio, we won't get that deep and mention GTP in there as well. As long as you can get what ATP is, understand that you've got the concept down, and it's the same exact concept there. So next then we have what we call electrical energy. Now when we talk electrical energy, you can see here electrical energy is going to result from the movement of charged particles. It results from the movement of charged particles. You'll see in our bodies, electrical currents are generated when charged particles that we call ions move along or across cell membranes. So when these ions, these charged particles, move across or move along a cell membrane, electrical currents are going to be generated. So it results from the movement of charged particles. And we're going to learn a lot about that because we're going to see the nervous system. The nervous system uses electrical currents that we call nerve impulses to transmit messages from one part of the body to another. In Bio 107, you've covered action potentials. You've talked about action potentials. Right? That's basically what we have when we talk about nerve impulses. Electrical currents traveling across the heart are going to stimulate it to contract, to beat, and allow it to then pump blood. So electrical currents, very, very important electrical energy is going to be. Skeletal muscle. Electrical energy there we're going to see is going to allow the skeletal muscle to go from an electrical event to an actual mechanical event. Where the skeletal muscle contracts, as we can see. Next then we have, after we talk mechanical energy, so mechanical energy then is going to be energy that's directly involved in moving matter. So in skeletal muscle you saw you went from electrical energy to then mechanical energy. So mechanical energy then is directly involved in moving matter. When you jog, right, your legs, they provide mechanical energy that moves you. And then the fourth form is radiant or electromagnetic energy. Now when we talk radiant or electromagnetic energy, you'll see this is energy that travels in waves. This is energy that travels in waves. And when we talk electromagnetic or radiant energy, this is going to be including visible light, infrared waves, radio waves, ultraviolet waves, X-rays. Light energy stimulates the retinas, and it's involved in vision. Ultraviolet, right? Ultraviolet light causes sunburns, but we do need a little bit, right, for the processing of a certain vitamin. My class, we cover that in anatomy. So one of the systems that we have in the body is going to be involved in helping to convert vitamin D eventually to its active form. But before it becomes its active form, it has to go through a few different systems. And the first system is the integumentary system, right? UV comes into basically the skin, helps to convert vitamin D to one form, and then that takes off and it makes its way over to then the liver. Liver then acts on it, converts it to another form. Then it makes its way over to the kidneys, and they're going to convert it to the active form. So here when we talk UV waves, the UV waves are going to cause sunburn, as I've mentioned. However, they also stimulate your body to make vitamin D. X-rays, they're beneficial, right? We have broken bones. We need to see what's inside the body. X-rays help out there. Okay, in the upcoming chapters, we're going to actually look at an electromagnetic radiation chart, and we'll see all these different forms of waves or light basically there, and we'll revisit basically the section there. Next, then let's move down, and let's talk then, and let's see here how it tells us energy may be converted from one form to another. So you saw that happen with electrical, then to mechanical. Now, energy conversion we'll see is inefficient. Some energy is lost as heat, and that's partly then unusable energy. Next, then here, so let's move down to the composition of matter. Let's talk about elements, and then we'll move down to atoms, talk about atoms. First, I'd like you to know about elements. When we talk elements, I want you to know first that all matter is composed of elements. All matter is going to be composed of elements. Elements are unique substances. They're unique substances that cannot be broken, down into simpler substances by ordinary chemical methods. There are some well-known elements, and they'll include oxygen, carbon, gold for me, right? Silver, copper, and iron. At present, 118 elements are recognized. Of these 118, elements are recognized. Of these, 92 occur in nature or naturally. Some individuals will say 94. We're not here to argue any of that. 93 is neptunium, 94 is plutonium. I think they're made too, but whatever. We're not here to argue that. The rest are going to be artificially made. Okay. Now, 4 elements. 4 elements we'll see: carbon, hydrogen, oxygen, and nitrogen. CHON, carbon, hydrogen, oxygen, and nitrogen are going to make up about 96% of our body weight, and about 20 to 24 others we'll see are going to be present in the body. However, we'll see smaller amounts. Here we can see out of all of those, these 9 are going to make up a greater percentage compared to the other than 11. So these you can see here are going to make up about 3.9%. And then the others we'll say are going to be found in trace amounts. They'll be found in trace amounts. Here we can see our periodic table of elements. Here I brought in a better one, one that's a little bit more complete. So here they're just showing you a few, right? We're not here to do chemistry. This is just one chapter in chemistry that we have in here, just to get you the basics, right? And you've seen most of the stuff you'll see from chem. And that's why chemistry is a prereq for this class. Now, when we go through and we talk, then let's talk atoms. Now, when we talk atoms, they make up matter. Atoms are building blocks of elements. They're building blocks of elements. Atoms are going to differ from element to element, and this gives the many elements that we're going to see their unique physical and chemical properties. So atoms are basically the smallest particles of an element with properties of that element. So smallest particles of an element that still maintains the properties of that element. Next is the atomic symbol. The atomic symbol we'll see is going to be a 1 or 2 lettered abbreviation for an element's name. It's usually we'll see the first letter or the first 2 letters of the element. For example, we'll see carbon we saw here. Its atomic symbol, I told you, is this capital letter C. When we talk hydrogen, this element, its atomic symbol is capital H. When we talk oxygen, capital O. Nitrogen, capital N. Calcium, capital C, lowercase a. So we said first letter or first 2 letters. Right, when we talk nah, this stands for nothing, right? Oh no, it says sodium. Doesn't make any sense. I just got through saying first letter or first 2 letters. So what about this then, Dr. Jalota? This says nah, right? No, it's Na. N, capital N, lowercase a, Na for sodium, right? It's the first 2 letters of sodium. Wait, what? What are you saying? It's not the first 2 letters. Oh, I think it's a typo maybe, right? No, I want you guys to know, in a few cases, the atomic symbol is taken from the Latin name. Okay, for example, sodium we see here is called natrium. So natrium, Natrium. That's where that Na comes from. Okay, some of them are going to be Latin derived. Next then, let's move down. Let's talk about the atomic structure. Let's talk about atomic structure. Now, when we talk about atomic structure, I want you guys to know atoms are clusters. Atoms are clusters of subatomic particles. Atoms are clusters of subatomic particles or smaller particles, which are called protons, neutrons, and electrons. An atom has a central nucleus that contains protons and neutrons, and they're tightly bound together. The nucleus is then surrounded by orbiting electrons. The nucleus is then surrounded by orbiting electrons. We can see that right inside of here. Protons and neutrons tightly bound in the nucleus. And here you can see your orbiting electrons. Protons, I want you to know, bear a positive charge. They have a positive electric charge to them. They carry a positive charge. And when we talk neutrons, neutrons, you'll see they are neutral. They're neutral. So the nucleus, then we can say, is positively charged overall, right? If only the protons are going to have a charge, the neutrons don't have a charge, right? They're neutral, we said. So the overall charge of the nucleus is going to be a positive charge. Next, then let's talk electrons. When we talk electrons, electrons are going to bear they're going to bear a negative charge. Electrons bear a negative charge. And that negative charge is going to be equal in strength. It's going to be equal in strength to the positively charged proton. It will be equal in strength to the positively charged proton. So we can say all electrons have a negative charge, protons have positive charges, neutrons have no charges. The nucleus we've established is going to have an overall positive charge. Now I want you to know all atoms are electrically neutral. All atoms are going to be electrically neutral. Why? Because the number of protons in an atom, the number of protons in an atom is balanced by its number of electrons. So the positive and the negative charges cancel each other. For example, hydrogen. Hydrogen, we can see here, has one proton, you see right inside of the nucleus, has one proton, which carries a positive charge as we've established, and it has only one electron. So you could see the positive charges are balanced by the negative charges. That is why we say that all atoms are electrically neutral, because the number of protons in the atom is going to be balanced by the number of electrons. So the positive charges and the negative electric charges are going to cancel each other. Next, then, we are going to see helium. Helium has two protons, two electrons, right? Because the neutrons, we said, they don't have a charge to them. So it's electrically neutral, this atom is. Here we've got lithium, right? 3 protons, 3 electrons. Electrically neutral. Iron, we move to iron. Iron we're going to be able to see then as well. Let's come back here. When we talk iron, iron you're going to be able to see now is going to have, do we have iron here, or do we have to go to the other one? So here we could see iron. Yeah, there not. Now when we talk iron, iron is going to have 26 protons. Iron has 26 protons, and it's going to have 26 electrons. So for any atom, the number of protons and electrons is always equal. In chemistry, then, they could go and complicate it and do all that. Again, we're not here to do chemistry, just get the basics down. Scientists, now, I want you to know, look, you'll see scientists are going to use the term orbitals to describe, you can say, the seats or the regions around the nucleus in which the electrons can be found most of the time. So when we talk about identifying elements, right, you're going to say, well, all protons are alike. Same is true for neutrons and electrons. Now, what you're going to say determines each element. So what determines each element? The answer is that atoms of different elements are composed of different numbers of subatomic particles by different numbers of protons, neutrons, and electrons. Hydrogen, we saw, for example, had 1 proton and 1 electron. And we saw lithium had 3 protons, 3 electrons, right? We're going to say, wait, protons are all the same, neutrons are all the same, electrons are all the same. This has protons, this has neutrons, this has electrons, this has protons, this has neutrons, this has electrons. Well, what's making everything different? You can see here, different elements are going to contain different numbers of subatomic particles. The simplest and the smallest atom is that of hydrogen. Hydrogen has 1 proton and 1 electron. Next in size is going to be helium. Here we can see this helium atom has 2 protons and 2 electrons. 2 protons and 2 electrons. We've also got, you can see there, 2 neutrons as well. But we're really going to be concerned more with the protons and the electrons for this conversation. And then eventually, we're really trying to learn more about these electrons, and we're going to apply electrons and how they're basically energy carriers, and they're going to be helping us to form ATP. So that's what we're really getting to. So again, now when we go through and we talk, all you really need to know to identify a particular element is the atomic number, the mass number. Let's do this over. So next in size is the helium atom. The helium atom has 2 protons. And we can see here 2 neutrons and 2 electrons, 2 radiating electrons. And then third, we've got lithium. Lithium, 3 protons, 3 electrons. Right? And we can see then we've got 4 neutrons, but again, we're not going to be really concerned with the neutrons. Now, all we really need to know to identify a particular element is its atomic number, mass number, and atomic weight. So let's talk first atomic number. When we talk atomic number, the atomic number of any atom is equal to the number of protons in its nucleus. Hydrogen has an atomic number of 1 and 1 proton. Helium, we saw, has an atomic number of 2, has 2 protons. Correct? Number of protons, 2. So the number of protons is always equal to the number of electrons we just saw, right? In an atom, because we said that they're electrically neutral. So the number of protons is always equal to the number of electrons in an atom. We can say then the atomic number indirectly tells us the number of electrons in an atom as well. So I want you to be able to understand that. I can give you a question where I tell you this is the atomic number. Tell me how many electrons are there. Next then is mass number. Mass number, the mass number of an atom is the sum of the masses of its protons and neutrons. So this simple knowledge is going to allow us to come up with the total number and the kinds of subatomic particles in any atom. We said the number of protons is the atomic number. The number of electrons also equals to the atomic number. And the number of neutrons is the mass number minus the atomic number. So for example, if I tell you the mass number is 40, the atomic number is 20, how many neutrons would you have? Right? The answer will be 20.